Good afternoon, guys. So today we're going to be talking about nonlinear models. And this is actually going to be the last lesson of chapter 3 that we're going to talk about. So let's go ahead and get started. Nonlinear models, when we talk about models, we do a lot of calculator work. We plug in data points and try to find a function that best models that data. So we're going to do that right here on this first problem. So let's get our calculators. And remember, we're going to use the same steps we use for linear and for quadratic models. You're going to hit the stat button and edit, and then we're going to type in these values into this list right here, okay? So let's plug in all the x coordinates into the L1 function or L1 table. So 2, 4, 6, 8, 2.5, 4.5, 6.5, 8.5, 3, 5, 7, 9, 3.5, 5.5, 7.5, 9.5. Get all those typed in, and then type in your y values: 1, 1.8, 3.1, 6.5, 1.2, 2, 3.8, 7.8, 1.3, 2.4, 4.5, 9, 1.5, 5, 2.5, sorry, 5, and last 10. Alright, so again, make sure that they line up. Once you get these big lists, sometimes you'll miss one and they won't line up and you'll know you need to add one in somewhere you missed something. Okay, so then once you plug your data in, we need to make sure our stat plot's on. So you hit y equals, and then go up to plot 1, hit enter, and that will plot all those points on your graph. If for some reason, if your stat list is not L1, L2, if yours is L2, L3, then you'll need to go to the stat plot button right here, and notice how it says L1, L2 on mine. You'll need to change those to L2, L3 down here. Okay, and of course your L2, L3 buttons are right here in blue. So you'll hit second, 2, second, 3. You need to change those to L2, L3. Alright, so now once you get your stat plot turned on, we want to look at the stat plot to see what shape it looks like. So we hit zoom. So let me get out of this first. So we hit zoom, and you hit 9 to zoom to see your stat plot. Alright, so when you plot these, you can see we get this shape right through here. And kind of the question we want to ask ourselves is what kind of model best fits this data? Alright, so it obviously has a little bit of a curve to it, right? So it's not really going to be linear. Linear is a straight line. So we can use maybe an exponential function because it looks like it's got that shape of an exponential, like an L shape going up. It could be a quadratic function. Maybe it's just part of a U shape. Another thing it could be is just a power function, which a power function is essentially just a function with x raised to a power. So that could be x squared, x to the third, some type of power function. So let's right here look and see which of these functions best fit the data. And the way we're going to do that is we need to turn on the stat diagnostics. So we need to go to mode, and you just scroll down and make sure that your stat diagnostics are turned on. And by that being turned on, that's going to give us a correlation coefficient once we do our regression equation. Okay, so once we see our stat, that looks like it could be an exponential or a power function. So let's figure out the model for each of those and see what the correlation coefficient is, and then we'll be able to know what the best model is for our data. So hit stat, calculate. Alright, now we've got a linear regression, quadratic regression, cubic, quartic. We're going to scroll down and look for an exponential regression. So let's do that one. Alright, got to make sure your L1, L2 are right, or maybe yours are L2, L3, so you need to change those if you have a different list. And hit calculate. Alright, so we see this is our model right here, and the correlation coefficient is 0.997. Alright, so when you have one that's pretty strong, right? 1 is perfect, so that's a pretty strong correlation coefficient to have. So now what we can do is try to do a regression on with a power function and see if it's got a better R value, better correlation coefficient. So we hit stat, calculate. Let's use a power function, power regression, same thing. And we see that this one gives us 0.96, so not as high as the exponential. So we need to go back now and find what was the exponential again, and we can record that as the best model for this function. So our model is going to be y equals y equals A, which is 0.507 if we round to the thousandths, times B, which is 1.368 raised to the x. And that will be the best model for that data, okay? Because it's got a better R squared value than an exponential function. All right, so I'm going to pause it, let you guys try the one down here below. Do the same thing, determine what's going to be the best shape for this function, and use the correlation coefficient to determine what's better. Okay, correlation coefficient we're looking at is the R squared value. Okay, the R squared, not the R. We're looking at R squared, 0.994, and the other one was like 0.95 or something like that. All right, so try this one. Let me know if you need help. All right, so similar to the last problem, we go to stat, edit, type all your numbers in. Once you got them typed in, okay, make sure your stat plot's on and hit zoom 9. You can see the dots on the graph. All right, and I've got a line already graphed on mine, but you wouldn't have that to start off with. And then after that, you can determine, it looks like it's got a curve to it, so it's going to be either an exponential or a power function. So then we do our stat, calculate, and you pick exponential power regression. Now, notice in here it says you want you to find an exponential model and a power model and determine use the coefficient determination for each model to determine which model is going to best fit the data. Whenever you plugged them in, notice it said T represent the year with T equals 1 corresponding to 2001. So when you typed them in, you needed to make sure that you put 1 for 2001, not 2001, 2002. If you do, you're going to get an error whenever you try to do your regression equation. So you got to plug in 1 right here for 2001, 2 for 2002, so on and so on. So once you do this, get your models. We see that the power model has a correlation coefficient of 0.9138, and the exponential correlation coefficient is 0.9991. Okay, so the next part says to graph both of them with the data. So that's what I've got here. This right here, this first line curving up is the exponential, and this one right here is the power. You can see the exponential is definitely following the points a lot more closely than the power function is, and that's kind of confirmed by our correlation coefficient. This one is a lot closer to 1, so the exponential function we expect it to fit the points a lot better. So our best model is going to be this right here, y equals 1,876.645 times 1.198 to the x, whenever we round to the thousandths. All right, so let's move on and look now at another example. Okay, so this table shows the yield in milligrams of a chemical reaction after X minutes. We want to use the calculator to find a logarithmic model and a linear model for the data and identify the coefficient determination for each model, determine what fits the data better, and use it to predict the yield after 20 minutes. All right, so same thing, we're going to type all these values in to our stat list. So just go to your stat list. You can type over the list, or if you go up and hit clear and then go back down, it'll just clear everything out. So you just go up to L2, hit clear, and drop back down, and it'll clear everything out. Don't hit delete, okay? Don't hit delete, just hit the clear button. So we got 1, 2, 3, 4, 5, 6, 7, 8. 1.5. 7.4, 10.2, 13.4, 15.8, 16.3, 18.2, 18.3. Alright, so now we're going to graph our points. Let's get these equations out of here. Hit zoom 9 to zoom stat. So you can see this shape. So it's got a little bit of a curve to it, or you could think maybe it's just a linear function right here. So we're going to see what fits it best. A logarithmic function, which has that curve to it, or would it be a linear function? Could be a quadratic, right? Maybe it's a U shape. So we gotta look and see which one fits the data best. They tell us just to check for logarithmic and linear. So we're not going to do quadratic, but it might be one that we would check also just to see if maybe it fits the data points a little bit better than one of the other two. So we'll go back, hit stat, calculate, and we'll do a linear regression first. So we get a correlation coefficient of 0.900, pretty strong, not too bad. And then we want to do a correlation coefficient for a logarithmic. So go to stat, calculate. And now don't get confused, this is logistic. That's not the one we're looking for. We're looking for logarithmic, which would be this right here, ln regression. Now you get a correlation of 0.993. Okay, so obviously this one is a better model. Okay, so we'd say the logarithmic model fits best. So to use the model to predict the yield after 20 minutes, we can either take this model and just plug in 20 for x, or we can graph it and look at the table. So we can go to y equals vars statistics, EQ regression equation, and we can graph it and see how close that line fits to the points. Pretty solid right through the middle of them. Now if you hit second table, right, we want to see what's the yield after 20 minutes. So that's this column, the x value, so we'll just scroll down to 20. And we see that the yield is 26.6 milligrams. All right, so that's how much will be yielded in the chemical reaction, 26.6 milligrams. All right, so you guys try this next problem right here. Let me know if you have any questions. All right, so there was a lot to do in this problem, obviously. You had to calculate a lot of different regressions, but essentially first step, just type in all your data. Once you've got the data plugged in, then you can look at the graph, see the dots, and start doing your regressions. So you had to stat, calculate, you had to do a linear, and then for the coefficient on linear, you got 0.9987. And B part, you had to do a power model, which was the one right here, and that gave you 0.95850. Then you had to do an exponential right here, and that gave you 0.9972. You finally had to do logarithmic, which is this one, and that gave you a regression equation of correlation coefficient 0.9803. All right, so then after that, they wanted us to determine which one out of those four was going to be the best model. So by looking at the correlation coefficients, you could see that the best model is the one that we found in part A, which was the linear model, okay, according to the correlation coefficient. Then they wanted you to graph them all, of course, and see which one, or what was the data going to be from 2009 through 2014. So we hit second table. Okay, you can see when we scroll down to 19, that's 2009, and 2014 is the year 20, or as when x is 24. So you can start here in the y values. This is your first function, the linear function, right? If we put do vars, vars, statistics, EQ, regression equation, for all four of these, we can put each one of them in a different y equals line and graph all four functions together. So then when we look at the table, we can see these are all the y values for the linear function. Y2 is all the y values we get for the power function, and then y3 is the exponential, and then y4 is the logarithmic function. So we can see all these values, and from there we can try to make an idea about which one makes the most sense based off of these numbers. So basically in the year 2024, logarithmic says there'll be 310 million people. The exponential function says 324 million, and then you've got 311 million from the power model and 322 million from the linear model. Okay, so this is kind of left up to you to determine which one looks the best. This isn't really far enough down the road to see what's really going to happen. Okay, so if you keep scrolling down, if you went down a little bit further, you'd start seeing this this gap between the exponential model and the linear model, those are getting a lot bigger than the logarithmic model and the power model. Okay, so you start seeing a gap, and if you graph it and zoom out from your graph, you can kind of tell what's going to happen. On this one, you can't really see it, but if you zoom out, okay, and you get a more zoomed out picture of what's going to happen later on down the road, you can see that this linear model is going to, of course, keep going up at a steady rate, right? Your exponential and logarithmic model are going to start kind of flattening out, and then, or your power and logarithmic model are going to start flattening out, and then your exponential is the last one that came in. It's actually going to start growing faster and faster. Okay, now with population typically starts to level out after so long. Okay, it can only grow at a fast rate for so long, and then eventually it's going to start leveling out. So over time, it's really not a good model to use the linear or the exponential, because they're not going to keep growing at that rate forever. Okay, eventually, limitations such as area of land, just different cultural things, it's going to level out eventually. It's not going to keep growing exponentially forever, because there's not going to be enough room for that to even take place. So it's got to level out at some point. So, one of these other models, the logarithmic model or the power model, would actually be the best model for this real world situation. But right there, the book says any answers can vary. So, whatever reasoning justification you found is fine. All right. So, moving on. So, fitting a logistic model. So, a logistic model is a situation kind of like population, where you're going to see a really big increase at first, and then the increase is going to start to level out. It's not going to increase at the same rate. The rate of increase is going to start to slow down a little bit. So to estimate the amount of defoliation caused by a gypsy moth during a given year, Forster counts the number of egg masses on 1/40th of an acre in the fall. The percent of defoliation Y the next spring is shown below. Use the regression feature of a calculator to find a logistic model for the data and figure out how closely does the model represent the data, and what would the percent be with 85 egg masses. All right, so we got to go through and take all this stuff that we had in here and clear it all out. And go to our stat list, clear out all this data, and start back. So we got 0, 25, 50, 75, 100, and we got 12, 44, 81, 96, 99. We zoom in on those points, and you can see it's kind of increasing quick, and then starts to level out, right? So sometimes you have the best model for a set of data is a logistic model. So we hit stat, calculate, and you can see right here a logistic model. So we can calculate that, and it asks how closely does the model represent the data. Well, we get our correlation coefficient on this one. Maybe we don't get a correlation coefficient on this one. So it must not give you one for logistic for some reason. So what we're going to do is graph it and see how close it looks like it's hitting the data. Bars, statistics, EQ, regression equation, and we graph it. And looks like it's hitting it about perfectly, right? So how closely does the model represent the data? We could say, it's near perfect or very well, something like that. And what would be the percent with 85 egg masses? So we hit stat table, and we're looking for X to be 85. So this might be one where we should change our table to scroll by tens. 85, so we'd say about 97.8% of defoliation is when you have 85 egg masses. All right, so go ahead and try this last one right here on your own, and let me know if you need help. All right, so we plug in these values, and notice it says let X represent the midpoint of the age group. So since they gave you a range of 20 to 24, you got to use the number in the middle of that, which would be 22. And then in the middle of this is 27, 32, 37, 42, 47, 57, and 67. So that's where we get the values to put in our table, and we put these Y values in. Of course, we go through the process of doing a regression, and we do a logistic model for the data, and then ask how closely does the model represent the data. So we have to graph it since it doesn't give us an r² value. And whenever we graph the function, we see that we should get a line that looks like this going through these points. And it looks like it's a pretty good correlation, not great, but good enough to where we could use this as a realistic model for the data. So that's a logistic model. Again, it's a situation kind of like this where it's growing quick over time, but it's got to level out eventually. Something similar to population has to do that. A lot of different things in real life follow logistic models of data. If you don't have any questions on this stuff, you can go ahead and practice some of these problems right here. Let me know if you need any help. And this will be the end of Chapter 3 for us.